Okay, this is my first attempt at standard 5.2. I decided to do 5.5, which asks to calculate the expectation values and the uncertainties of position and momentum for the infinite square well energy eigenstates. We know we can determine the expectation value through finding the weighted average of the product of the probability of finding the electron at a certain position in the well. This can be done through the following math here. We use the allowed energy eigenstates for an infinite well as well as the wave function to find here this. We know the expectation value will be the same for every eigenstate of the system. Using this fact and plugging in our previous finding, we can solve for the expectation value of a particle in the square well. Since every eigenstate gives us the same result, we use the ground state since it's the easiest. This can be found here. And we end up finding that the expectation value is L over 2. We know the average position measurement should be the midpoint of the well since there's no preference to the left or right side. And we also get the equation of the momentum operator from our textbook right here. Again, we solve for the expectation value for momentum in the same way as before. We can take a spatial derivative and use the u sub u equal to pi x over L to solve for the expectation value of momentum, and we find that it is equal to 0. This makes sense if we consider the particle in the box as a standing wave, which would have no net flow of energy. We calculate the uncertainties through standard deviation. In order to use this equation, we first must find the expectation value of x squared. So that is simply shown here. And then using the same sub as earlier, we solve that the expectation value of x squared is 0.283 L squared. Thus, we can plug back into our standard deviation formula to find that the uncertainty in position is 0.182 times L. To solve for the expectation value of p squared, we do the same thing as above. We have this formula here. We use the u sub pi x over L to solve this integral, and we get that the expectation value of p squared is h bar squared pi squared over L squared. Again, we plug in to our standard deviation formula to find that the standard deviation, the uncertainty for momentum, is h bar pi over L.